Well, thank you all for coming to this talk. This is partly motivated by physics, partly a little bit by neuroscience. All right, so here's the outline. So there's a reference there to a paper, well actually it is a PhD dissertation by Furey, who was actually here. She gave a talk at a physics conference that I attended and got interested in some statistical questions related to what she was talking about. And I'll give you some background about her idea, which is a very elegant idea, I must say, and I think well, I'll defer all the physics questions to Paul. So the aim actually, from a statistical point of view, is to develop probabilistic results about large tree diagrams, edge-weighted tree diagrams. The weights on the tree are not random variables in the traditional sense. They're going to be free random variables. This is going to be in the setting of non-commutative probability. And that allows us to, for example, consider edge weights that are elements of algebras. They could be matrices, large matrices. Therefore, there's a non-commutative aspect to the problem. And I'm interested in basically the sum of the paths in such tree diagrams. I'll give you a background on what these tree diagrams look like. And are there any interesting limiting results that we can get coming out of these trees? These are going to be standard limiting distributions. And the bottom line is, indeed, we find Marchenko-Pastur distributions, we find Wigner semicircle distributions emerging as limits from these trees. Sums over paths in these trees. So in a nutshell, that's what I'm going to tell you about. And it's a bit surprising because these very famous limiting distributions for large random matrices. When we say large random matrices, these are classical, under classical probability. We're in a rather different setting. So we're in these tree diagram settings, and there's actually, they're not random in the traditional sense. And I'll explain what I mean by non-commutative probability and the sense in which these are random. All right. This is also, there's a quantum probability aspect of this. In fact, the rules of probability are under the quantum setting that we're going to look at. And there is a biophysics motivation. As you may notice, I don't have it here, but I am in a biostatistics department. So I need some bio motivation. And this is a rather speculative connection with some neural qubit models that I'll tell you about as well. All right, so this is the particle physics motivation. This is the idea of Cole's work. And what she proposed is that the basic ingredients, indeed particles themselves, emerge at a very fundamental level from a sufficiently rich algebra acting on itself in some sense. And these algebras, I'll give you some examples, but she can tell you more about the algebras. One particular case is the complex quaternions. So a tensor product of the standard complex and the quaternions, and you can get a lot of the fundamental objects in the standard model out of that. Now the standard model is a tremendously complex thing, which I can't explain to you, but there are lots of ingredients. Space-time, of course, Fock space, there's matter fields or wave functions, you might call them. The Higgs field, the gauge field, or local coordinate systems. So tremendously complicated, and Cole's idea is indeed what are the minimal assumptions that may produce all this very rich structure in some sense. All right. So she also proposed that causality itself can arise out of very simple structures of this type through the evaluation of algebraic expressions. And this is a picture to explain that idea. So I'll call these causal tree diagrams because we're going to be talking about trees. So here's a very simple tree, rooted tree. So you can think of an algebraic expression encoded by this tree diagram as a sum over paths, all the paths leading from a leaf to the root of the tree. And you, as you see, as you move up through the paths, multiplying along the edges, these are edge weights, which can be in a general algebra, as long as we have a multiplication and addition operation for our algebra. Here we have the product ABC. You see that's going to be the first term. These are non-commutative multiplication here. So as you see, it depends on the particular order in which these appear on the path leading to the root of the tree. So there are only 4 paths leading to the root. Here's the final path here. But we operate from the leaves of the tree up to the root, and you could think of that as the evaluated algebraic expression as representing something. But the point is, in terms of causality, once you've evaluated this expression, there's another element of the algebra. We've lost all information about the ingredients that went into it. So that gives us, in a sense, an arrow of time. So time itself could be an emergent property of such a system. And that's why we call them causal trees, because indeed all these ingredients are causing, once this expression is evaluated, we have an outcome, if you like. So it's not causality in the statistical sense, but causality in a physical sense. So this very elegant idea is due to Cole in her dissertation, and there are related ideas, but more complicated ideas. So in her idea, these particles emerge at a fundamental level, whereas these I think they come out of information. Particles emerge from information theory ideas in a much more complicated way. So this is a very elegant approach. All right. So the second motivation, which is a highly speculative idea, so bear with me about this, but it is grounded in some very elegant physics as well. So the question is, does the brain function like a quantum computer? A very provocative question. A lot of there's been so much speculation about this question, certainly in the last 20 years. The fundamental difficulty is, of course, the brain is wet and warm, and so any quantum entanglement is likely to disappear, decohere very quickly. So it's hard to imagine, indeed, in such an environment, there could be any quantum effects. Nevertheless, I'm going to refer to this paper in the Annals of Physics by Matthew Fisher, who's a famous physicist, and he basically phrased the question in these terms, and he came up with a proposal to find an isolated nuclear spin that can operate as a qubit, a quantum bit, if you like. He wants a mechanism for entanglement of such nuclear spins, a mechanism for quantum processing. In other words, so it's not just enough, of course, there should be quantum processing, but it also has to transfer into biomechanical outputs through a synaptic mechanism. So Fisher's proposal is indeed that phosphorus atoms could function as neural qubits, and the reason there's a very fundamental reason for this, that the nuclear spin of a phosphorus atom is 1/2, and that's the lowest it can be. And therefore, that means it's unlikely to decohere. And qubits are unlikely to decohere in the warm and wet environment. Lithium also has a sort of honorary 1/2 nuclear spin, and it's well known that the lithium is a treatment for various polar disorder, schizophrenia, and so on. So, and that's thought to be, well, it's conjectured to be due to the nuclear spin of 1/2. All right, so this is a schematic from a journal, a popular New Scientist journal, magazine showing Fisher's idea and how. So these phosphorus atoms in molecules called Posner molecules. Here's the formula for these molecules. There are 6 phosphorus atoms in each of these molecules, and they can entangle between different molecules. They can be indeed entangled. There's evidence of that. And in the presynaptic region, they could be entangled. They could be entangled across synapses. And if one of them, so one of these Posner molecules melts, if you like, releases its calcium. There are calcium ions as well in this complex. That can cause a neurotransmitter across a synapse. So we can get synaptic interactions across different synapses, basically. And that's sort of the idea. That's probably enough of the idea. All right. Now, how about trees? So I was telling you I'm going to talk about trees and random weights on trees. Well, there is certainly evidence of trees in the brain, especially in the motor cortex. The motor cortex is largely organized with neurons with very large dendritic structures. And even the neurons are organized in trees because of the voluntary nature of the motor cortex. Unlike the sensory cortex, where there are very complicated networks, in the motor cortex, it's essentially they're organized as trees. So there's also, of course, good evidence for that. Another idea I want to briefly touch on is again a speculative idea, the so-called critical brain hypothesis. And this has sort of been floating around, well, at least since a fascinating paper of Turing, 1950, the famous imitation game paper, of the movie's name as well. And I'll show you a quote from that paper. But the idea of the critical brain hypothesis is that basically the brain operates most effectively at a critical level. So it could be slightly critical, subcritical, or slightly supercritical branching processes could describe the human brain in some sense. There's an enormous literature on this, but I would say it's still highly speculative. Here's actually a quote from Turing's imitation game paper, and I'll let you read this for yourself, but I want to mention that he talks about a chain reaction, a branching process, basically, as an analogy for the way the brain may operate. So it's an intriguing idea, and this paper of Turing is cited even very recently. This is a 2016 paper about phase transitions in networks of neurons. These are not quantum neurons, but these are, so it cites Turing's initiation of this field of what's called organized criticality. So the brain may operate at a most efficient level at a critical point. So these are sort of ideas that are floating around in the neuroscience literature, which I will sort of touch on. So again, motivation. Now let me formalize some of these ideas. Well, formalize them in a possibly rather artificial way, but nevertheless, I think a useful way to think about these problems. And I'll give you the background on classical trees of this type. These are called multiplicative cascades, random multiplicative cascades. They were introduced by Mandelbrot in the 1970s. He was interested in fractals, of course, and in particular, the fractal nature of turbulence. So I'll call these causal trees for the reason the physics connection, as I mentioned earlier. So I'm going to talk about very regular trees with just a fixed number of vertices. So capital N will denote the number of vertices. This will be a binary tree. So at the root of the tree we have two edges and so on. So every vertex has 2 edges. Here's a three-partite tree with every vertex having three edges coming out of it, emerging, or three children. So big N is the number of children. And on each edge, let's put a non-negative random variable, classical non-negative random variable with mean 1. And, well, what's the large scale structure of these things? So these sums, so we get what the physicists would call a partition function by summing all the paths over these edge weights. So this idea was developed partly in the physics literature. Here we go, this paper, rather famous paper, DeRita and Stone, 1988. They were interested in directed polymers, in disordered environments, and so more in the mathematical literature now. So just to formalize the notation here, let's use this notation for the tree itself, the infinite tree. Okay, so a word, what is a word? It's a path basically from a leaf to the node of the tree. Okay. Self-avoiding path. Okay. It can go either way, of course, from the root to a vertex or vice versa. Okay, so given such a sequence, so we're going to label the edge weights here in an obvious way. So for the first, this is binary tree, W1, W2, then we add indices as we go across the tree, as you see in this fashion. So this is basic. Try and keep this notation somewhat in mind, because I'll use this notation later. So what is known about the continuum limit of such trees? So this is a result due to Mandelbrot in those papers I mentioned. So we're in the n-ary tree. If we look at the height n, so we're going to go down the tree in steps, in generations. The sum over paths, we're going to normalize it, of course, by the total number of paths, which is this, big N to the little n. It has an almost sure limit. So here's the normalized sum over all the paths, multiplying edge weights as we go along the path, and then summing over all the paths. Normalized by the total number of paths, and that converges almost surely to a limit, a limiting random variable non-negative xn, almost surely, and this is simply a consequence of the Marchenko convergence theorem, because this is easy to see. This is a non-negative, well, it's non-negative, it's a Marchenko, and therefore it has an almost sure limit. This is the Marchenko property. Okay. So of course we want to understand what this limit distribution looks like, and that's the real challenge in this area. So to derive that result, the fundamental idea is a recursion relation, a distributional recursion relation, or fixed point equation. And that just comes from the tree structure. So this is the fundamental recursion relation that Mandelbrot derived, and it's just a simple consequence of this picture, if you like. So let W1 through W big N be IID according to this edge weight distribution, and let Xi, N be independent copies of Xn, the limiting random variable. And then we must have this recursion relation, right? Because as you can see that as we go one step down in the tree, we get this recursive property. We get another copy of the tree coming one step down. So we get a weighted average of these two trees here. That's what so Xn plus 1 is exactly this whole thing. That is the weighted combination of these two smaller trees. as n goes to infinity, of course, we get actual agreement here in the limit. Okay, so now you may ask, well, how do we solve this recursion equation? It's a very hard equation to solve. In fact, there are not many concrete examples. One known example is if the edge weight, normalized edge weight distribution is a certain beta distribution, then the limiting distribution is gamma with certain parameters. So that's a known example, but there are not many. There are general results about the nature of the limiting distribution. This is a very famous result, 1976, Kahan and Perrier, that identified the phase transition structure. So there are two regimes that the limiting distribution has mean 1 if this condition holds. This is a kind of entropy condition. Typically, physicists, of course, would actually pose this in terms of these edge weights would be e to the minus beta of some distribution, and the beta would be an inverse temperature. So this would correspond to a high temperature condition. So we have a high temperature regime under this condition. Otherwise, the limiting distribution is degenerate. Xn is 0 almost surely. That's a freezing state. Now, if you're interested in the distribution in the freezing state, you would have to do a different normalization from our normalization, which was normalizing by the total number of trees. But you have to do a less severe normalization to get a non-degenerate limit in this case. All right. There are some elegant results of Duret and Liggett that also find properties of the non-trivial solutions in terms of Laplace transforms. There's also a central limit theorem due to Liu and Rual that shows that if you let the number of children go to infinity, so you get this central limit with a normal limit result. So I'm only mentioning these because I'm going to give you an extension of this result in a little bit. Okay, this result we can't extend. This is a classification of the phase transition, and I can't identify phase transition in this quantum setting that I'm looking at. But I'd say there's a very large literature on this, probably 50 papers even since this time. Right. So what are the results that I have? So this is just a brief summary, and I'll go into detail in a minute. So I'm going to use this notation. WA bar is going to be the normalized edge weight. It's convenient to normalize by the number of children at each vertex. So if indeed that normalized edge weight is, if those normalized edge weights are Bernoullis, freely independent Bernoullis. I'll tell you what that means in a minute. But basically, Bernoullis with success probability 1 over n, their distribution is going to be just classical Bernoulli, but they're going to be freely independent. So of course, the edge weights themselves then, of course, have expectation 1, which is what we need. All right, then the solution of the non-commutative version of that recursion relation is Marchenko-Pastur with parameter lambda equals 1. That's going to give us mean 1, and we get convergence of the sum of the paths in distribution in the usual sense to the Marchenko-Pastur. So that's the key result that I have. I think it's very interesting. As I say, this Marchenko-Pastur arises out of limits of large random matrices, Wishart matrices for statisticians, and this is an unusual connection. So this actually is in strong contrast to the classical case. The classical case I just mentioned, if indeed the edge weights the normalized edge weights are classically Bernoulli, 1 over n, classically independent. Then the sum of the powers has a degenerate limiting distribution. You can see that just checking that condition that I mentioned, the Kahan and Furey condition, that entropy condition. So remember, here it is. We need in the high temperature phase, to get a non-degenerate limit, we need a strict inequality here. But it's as you can see, this expectation is precisely log n, so we do not have a strict inequality. So we have a degenerate limit. We're in the low temperature phase, classically. But here we're very much. So what is it about this non-commutative setting that gives us a non-degenerate limit? So, and then the other result I have that I will talk about is the Wigner semicircle law limit, the central limit result. Now this is not surprising because the Wigner semicircle law plays the role of a Gaussian, the standard Gaussian distribution in non-commutative probability. So we have this result so this is if the edge weights have a fixed distribution, not depending on the number of children, and we let the number of children go to infinity. So this is trees that this is just so we've already let little n go to infinity. We're in the infinite tree, but now we let the number of children go to infinity. So we get that. Okay, so those are the results that I have. I can take a pause here if everybody understands everything so far. I guess that's fine. I could take questions, or I can continue. But certainly stop me if anything's mysterious. But that's the summary. And so a little more background now, just to fill in details. This is the limiting distribution, the density of the Marchenko-Pastur with mean 1. So the scale here is a bit deceptive. It's a very flat distribution supported by, on the interval 0 to 4, with a singularity at 0, mean of 1. So this is what I find in that the Bernoulli edge weight case in the free probability setting. This is the density here of the sum of the parts. Okay, so that's, and then for those of you who haven't seen the Wigner semicircle law, in our case, well, we have radius varying. The radius is defined in terms of the variance of our edge weights. But the classical standard Wigner semicircle law is this one with radius 2 here. It's not quite a semicircle, it looks more like an ellipse. And actually the square of the semicircle random variable with radius 2 agrees with the Marchenko-Pastur with mean 1. And that's the connection. All right, so some background on non-commutative probability. I'm not an expert, I should say, in this area, but I've learned it somewhat in the last few months as I've been writing this paper. So what is a non-commutative probability space? So I'm using analogous notation to the classical notation of classical probability, E for expectation. This is not always used in the mathematical literature, but for statisticians, it's nice to think about the E as being an expectation. And in the physics terminology, E is called a state, and it's simply a linear operator from an algebra to the complex plane. It's a linear functional, and it's the expectation of the identity, multiplicative identity in the algebra is 1. So you can think by analogy that that's the standard properties of classical expectation. The state sometimes is what we call the wave function in quantum mechanical language. It can be the Born rule will allow you to evaluate expectations of observables. Observables are random variables, we would call them in probability. Physicists would call them observables. An observable may be, well, what is an observable? It's an element of our algebra. At this point, I haven't given you any structure of the algebra, but it will be a von Neumann algebra. In other words, it'll be an algebra of bounded linear operators in some Hilbert space. We'll get to that in a minute. But imagine, it could be these could be large matrices, if you like, collections of large matrices. But X is simply, so you can think of X as a matrix, or you can think of it as a bounded linear operator in a Hilbert space. There's an adjoint operation. So these are what's called star algebras, is an adjoint. All right, so this is basically the structure. So observables we'll call the observables non-commutative random variables. We have centering, of course. We can center any of them given their expectation. They all have expectations, right? So that sounds a little more restrictive than classical probability, where we don't have to always have expectations or moments. But here we will. So this is the notion of centering. This will have, of course, expectation 0. Non-negative random variables have this form, or positive random variables is the standard terminology. We have this form, an adjoint of X times X. So classical probability is the algebra is all bounded, measurable, real-valued functions on some probability of space, and this is the linear map, usual expectation. So that's classical probability. Now, as I mentioned, the algebra in the quantum mechanical setting will be a subspace of all bounded linear operators on some separable Hilbert space. The involution will be the adjoint operator, the adjoint operation on these operators. We need some other conditions. We need to assume the state is tracial, so we take expectations of products we can commute. Now, of course, this is a non-commutative multiplication here. So X times Y is not the same as Y times X, but in expectation, we assume they're the same. That's not a strong condition. We have, we can define a linear map from the set of all polynomials in X with complex coefficients, just in this fashion. So this is, of course, defines all moments, if you like, of the observable. And if we assume that we have a normal observable, a random element, this satisfying this condition, then there is a unique probability measure on the real line, a spectral measure, a spectral distribution, such that this law is represented by that measure in this sense. So that therefore gives us notions of convergence and distribution if the spectral distributions converge in distribution in the usual sense. So when the law, we have a sequence of random variables in this sense, when it's determined by its moments, when these laws are determined by their moments, then of course convergence and distribution in this sense is equivalent. You adopt the standard definition of convergence and distribution. All right. Now what really makes this theory take off is work of Voiculescu in the beginning in the 1980s, late 1980s, and this definition of non-commutative independence called free independence. And it's worth spending a minute or so to tell you about this. So we first define independence of a collection of algebras, subalgebras of our big algebra A. So we say that a family of algebra, of subalgebras, are freely independent if, whenever we take a finite product, x1 through xn, of centered, these are centered random variables, zero mean, and these are alternating products, so we never repeat membership of these algebras, right? So these have to come from, as we move down the sequence, they have to come from different, each time we go to a new one, it has to come from a different algebra, subalgebra. then that product has zero mean, is also centered. So we have, these are all centered, and this is a so-called alternating product, then it is also centered. So that's the definition of independence in this setting. It's not the same as classical independence. You could say classical independence will have this property, but not vice versa. So if we have a sequence of random elements, that is free if and only if the generated algebras are free, of course. So this is not a general, this is a distinct notion of independence from classical independence. And to see that, so suppose we have classically independent random variables, x and y. So let's consider the product and say they're centered. So let's look at the product of their variances here. Well, they're classically independent, so we can write this as, we can reorganize the expectation like this. But if they're also free, then this must be zero by this condition we just talked about. Right? So that means the product of their variances is zero. That means one of them must be degenerate. That is mean. So you can see that the property of freedom basically is very distinct from classical independence. All right. So we can't use notions of classical probability. Certainly we can't use classical notions of characteristic functions to get limit distributions. So the role played by the characteristic function is now played by the Cauchy transform or the Stilches transform, defined here. So if we have, in particular, we're interested in the distributions of the sums of random variables and the products of random variables in our case. So we need to be able to find their distributions. And here's the free convolution, free additive convolution notation. So if we have x distributed mu, spectral distribution mu, y distributed mu, then this is the multiplicative convolution notation. We can derive expressions for their various transforms of these distributions. First of all, here's the Cauchy transform. It's an analytic function from the upper half of the complex plane to the lower half of the complex plane that uniquely determines the distribution mu. And Wojciechowski introduced this R transform idea. So you take the Cauchy transform and basically invert it in some sense. You take out the leading 1 over z term, the pole, and this is the R transform, this remaining part of the universe. It's well defined. It's uniquely determined in some neighborhood of the origin. And for compactly supported distributions, the R transform of the additive convolution is the sum of the R transforms. So we also use this variation on the R transform, simply multiplied by z, and that can be expressed in this form in terms of the Cauchy transform. There's also a very, very helpful transform for the multiplicative convolutions known as the S transform, defined here, the inverse of the R transform that I just defined here, divided by z. And that also uniquely determines the distribution. If you have a distribution which is not degenerate at zero, then the multiplicative convolution with any other distribution is non-degenerate. And this is the relation between the S transform of the multiplicative convolution and the individual S transforms. So you can see this is going to be useful to us as well. So back to these causal trees. Yes?
Are any of these transforms useful in normal classical probability?
No, these are, well, I would say the Cauchy transform, the Stilches transform, is very useful in random matrix theory, yes. Yeah. In random matrix theory, they generally, they usually call a variation on this the Stilches transform, and that is very widely used, yes, absolutely.
RNS?
I don't think so. I haven't seen the RNS used in random matrix theory, per se. Although, or in large random matrices, in certain settings, are indeed freely independent. So they do play a role, but I would say in the statistical literature, the probabilistic literature, I haven't seen these particularly playing a role yet.
So for simple random variables, can you remember what the RNS transforms look like?
Oh, these are, they're defined, the
Sure.
Cauchy transform, yeah. Oh, so you can define, these are defined for any distribution.
Right. So
Right,
for
so
Gaussian,
they're
what is the
they're
R
certainly defined, yes. We're talking about distributions on the real line.
Right.
Yeah. So everything is defined. And, but what is the role of this in classical probability? That's not clear. This is purely this is the of course the analog of the Fourier transform, but in the free probability setting. But notice that of course you don't multiply you add the R transforms. And when you look at the multiplicative convolution, you multiply the S transforms. Okay. So back to our, so remember this was the notation for the sum over paths we were looking at, normalized sum over paths. Now we want to characterize this in terms of the free probability setting, where the edge weights are now freely independent. So we re-express this thing. We break it up into sort of an iterated sum like this, and you can see within. So each of these will be a well-defined random variable in the free probability setting, and it will have a well-defined distribution. And moreover, because these remember the edge weights are freely independent, so this is a well-defined has a well-defined distribution using the those formulas I just talked about, and then we have these products here, and these are products of freely independent objects. So this has a well-defined spectral distribution.
So can I think of it as a product of random matrices?
You could think of it indeed like that, but really very, very large random matrices. Okay, so remember we used this normalized edge weights. That was the W bar notation. So I'll use nu for that the distribution for the normalized edge weights. Right. So one of the conditions for this to work, yes. So these edge weight distributions have to be non-negative or positive elements of our algebra in the way I defined. All right. So these have non-negative elements of normal. So we have well-defined spectral distributions on the positive real line. Okay. So what's the analog of that recursion relation? Here it is in terms of these multiplicative and additive convolution notation. So this is the normalized edge weight distribution multiplying mu. So that recursion relation really is it's the limit of the iterates of this map that I'll call the free Mandelbrot map. So we have a fixed point of this map here, and that's going to define a solution to the recursion relation, as you can see. So the 1 over n is sort of absorbed in here, the 1 over n that we had in our previous recursion relation. But now we have the free convolution, multiplicative convolution, the free additive convolution here, n times, because we have n terms. So that's clear. So we have to be able to find a fixed point of this map, this Mandelbrot map, we'll call it. Well, the question is, do these things exist? Can we construct in algebra and freely independent Bernoulli edge weights. My main result, of course, talks about freely independent Bernoulli edge weights. And the way to construct these things is to use a Fock space. This is an infinite direct sum of tensor products of really smaller, much smaller spaces, products of the copies of the complex field and the complex plane constructed in this sense. So Fock spaces are very important in quantum field theory, but I won't go into them here. But here the actual ground state of our system. This is, remember, the expectation for statisticians is defined in this sense for any observable x. Omega here is what's called the vacuum vector. It's this vector here in the complex, and this can be defined. We have observables defined by these 2 by 2 matrices, and these are extended as embedded as linear operators on this Fock space. This is a very toy example of a Fock space, by the way. It's just enough to give us freely independent Bernoullis of the type we need. It won't give you, say, freely independent Wigner random variables, which are also important. Okay, so this is enough to get the freely independent Bernoullis. You can actually check. You can actually find the moments here just by taking powers of these 2 by 2 matrices. N to the k minus 1. This agrees with the kth moment of this. This is the n times the Bernoulli 1 over n. So therefore, the normalized edge weights have Bernoulli 1 over n distribution. Okay. So the main result that I mentioned earlier, we're running out of time now, but this is the first result that I have. This is a general result. If you know that Mandelbrot map has a unit mean fixed point determined by its moments, then we get a limiting distribution, the existence of a limiting distribution. I'm not saying the form of this limiting distribution. All I know is that it exists. It could be degenerate. It may not be. But that was the classical result. The open question is, of course, do we have an extension of the classical result of Kahan and Perrier? I don't know. That's an open problem. But we do know there is a limiting distribution, and that can be proved using an extension of the Martingale convergence theorem to this free probability setting. Now we're to actually, in the special case of the Bernoulli edge weights, we want to know, is there a fixed point of the Mandelbrot map? And indeed, this is a fixed point of the Mandelbrot map, and we do get convergence of the edge weights to the Marchenko-Pastur. So that's the earlier result I mentioned. And just some remarks and some connections. Marchenko-Pastur is also called free Poisson because it can be the free additive convolution of Bernoullis in this sense, which is, of course, analogous to the classical Poisson limit. In the classical case, as I mentioned, you get a degenerate limit here. Now, we can think of the Bernoulli edge weights in this tree as representing a Galton-Watson branching process with an offspring distribution, a binomial offspring distribution. So remember, there are n possible children. So we have a binomial 1 over n as the offspring distribution in a Galton-Watson process. This is the critical case because the mean number of offspring is 1. Okay, we'll do that later. And as you know, the population dies out with probability 1 in the critical case. Now, so in the quantum setting, of course, the Galton-Watson branching process theory was reinvented in the 1930s by Szilard, working with Fermi, actually at Columbia, and they were interested, of course, in nuclear fission and understanding when a nuclear reaction would go critical. And the interesting thing is, of course, it really, at criticality, it dies out, the classical Galton-Watson process. It's only at a supercritical case where it really goes critical. But in this quantum probability setting, we have, at a critical point, the classically critical point, it does not die out. There's a non-degenerate limit, the Marchenko-Pastur limit that we were talking about. Okay. And then, well, I'm wondering, this is a question for Cole here, indeed, does that have some implications for in the particle physics setting? And does it have implications for the neural qubit setting that we talked about earlier? So that's why I introduced some of those neuroscience ideas about tree structures and entanglement between neural qubits. But as I say, it's highly speculative, and but it was motivation. And well, here's the proof of that theorem, the second theorem about the Bernoulli edge weights, using basically, as you can see, it's just writing down the Cauchy transforms. Here's the Cauchy transform of the Marchenko-Pastur law. And then you can simply find its R transform and its S transform, taking these very nice and simple forms. The S transform of the scaled Bernoulli is this. So therefore, now you can find the S transform of the multiplicative convolution of this Bernoulli with the Marchenko-Pastur, just taking the product. And there's a very nice cancellation. So once I saw this nice cancellation, okay, that's helpful. So if there's any depth to this, it's canceling. Yes. Okay, and then you recognize this as the S transform of Marchenko-Pastur with parameter 1 over n. And then, so we have this result. So then we can find the R transform of the additive convolution of n copies of that by just adding them up. The n cancels, we get that. That's the R transform of Marchenko-Pastur. That's it. So we've shown that the Marchenko-Pastur satisfies that recursion relation. It's a fixed point of the Mandelbrot map, as required. That's the proof. So the other theorem I won't prove. I'm almost out of time. Here are some of the references. Here's Cole's PhD dissertation here. Got me started thinking about this. The classic paper of Kahan and Furey and Mandelbrot's papers as well. So that's it. Thank you very much.